Hi everyone. In this video we're going to review Gibbs free energy as well as reaction coordinate diagrams. Alright, so you might recall that the Gibbs free energy measures spontaneity. So for instance, this will tell us if a reaction does occur. And I'll add to that, does a reaction occur naturally or spontaneously? So for instance, some reactions don't occur unless you add a lot of energy into them. So those would typically be called non-spontaneous reactions. Reactions that just occur all on their own without any outside help are considered spontaneous. So the equation for Gibbs free energy is delta G, so that's Gibbs free energy, is equal to the enthalpy minus temperature times the entropy. You could also write this as delta H plus negative T delta S. Sometimes that helps, and we'll see why later. But in general, if delta G is negative, then the reaction is spontaneous. And if delta G is positive, the reaction is non-spontaneous. Okay, so now let's relate this to some energy diagrams or reaction coordinate diagrams. All right, so let's draw some X and Y axes here. And on the y-axis, we have energy. So it's increasing, going up. And then on the x-axis, we have reaction progress. And I'm just abbreviating reaction as RXN. So let's say we start with reactants that are pretty high in energy, and I'll just label those with an R. So these reactants are fairly unstable, and then they have to go over an energy barrier to get to the products, which are really low in energy. So the products are fairly stable relative to the reactants. So there's a couple of terms you might remember from general chemistry. So the difference between the reactant energy and the top of this barrier is called the activation energy. And this is abbreviated EA. And then the difference in energy between the reactants and the products is called Gibbs free energy. Oh, delta G, Gibbs free energy. Now, looking at the Gibbs free energy there, it's decreasing. So it's going from a really high energy to a really low energy. So that tells us that delta G is negative. So this reaction is losing heat. So this would be an exothermic reaction. And delta G is negative, which tells us that this is a spontaneous reaction. Okay, so what if the reactants and the products are flipped? So what if the reactants start at a lower energy and the products are at a higher energy? So let's draw that diagram. Okay, so let's say our reactants are at a lower energy, and then they have to get over this barrier to get to the products, which are at a higher energy. So again, the difference in energy between the top of this barrier and the reactants is the activation energy. And then the difference between the reactants and the products is the Gibbs free energy. So in this scenario, delta G is increasing, so the energy is going up. So this reaction is gaining heat, which means it is endothermic. So delta G is positive, which is non-spontaneous. All right, now these are very simplistic diagrams for reactions. There are cases that are a little more complex, so let's talk about those cases. All right, so let's talk about the Gibbs free energy reaction again, or equation, excuse me. And I'm just going to write this out as an addition as well. Now, what if our enthalpy is negative and our entropy of the system is negative? Is delta G positive or negative? So is the reaction spontaneous? Well, let's kind of plug those in. So if delta H is negative and delta S is negative, well, let's look at negative T delta S as a whole. So here we have a negative times a negative. So this whole thing would actually be positive. All right, so we have a negative enthalpy, and then negative T delta S is actually positive. So is delta G positive or is it negative? So in this case, it actually depends on the temperature. All right. So, let me add delta G depends on magnitude of temperature in this case. So let's actually make a little table kind of going over all of the different signs that can occur. So down below, we'll make a table of delta H, delta S, negative T delta S, and then delta G. Okay, so let's say delta H is positive, delta S is positive. Then let's say delta H is positive, but delta S is negative. And then we'll say delta H is negative, but delta S is positive. And then delta H is negative, but delta S is also negative. Okay, so we have all of our different scenarios here. All right, so if delta S is positive, would negative T delta S be positive or negative? It would be negative, right? Because delta S is positive and then times a negative gives us a negative. So let's see, let's plug that in up above. Okay, so we said that delta H is positive and then negative T delta S is negative. So is delta G positive or negative? Again, it depends on the temperature, right? Okay, so remember, delta G is negative for a spontaneous reaction. So let's try to figure out, when is delta G negative? Is it negative at high temperatures or at low temperatures? At high temperatures. So delta G is negative at high temperatures. All right. So now let's look at our second scenario. Let's say that delta H is positive, but this time delta S is negative. So if delta S is negative, what is negative T delta S? Is that negative or positive? Positive. Okay, because we have a negative times a negative, right? So now let's write those in up above. So delta H is positive, and then negative T delta S is overall positive. So if we have two positives, what is delta G? Positive. And this will be at all temperatures. So in this scenario, the magnitude of the temperature doesn't really matter. So if your reaction is endothermic, and then your change in entropy is negative, so the order is increasing, so your disorder is going away, then that tells us that delta G will be non-spontaneous at all temperatures. Okay, so now let's look at our third scenario. We have a negative enthalpy and a positive entropy. So if entropy is positive, what is negative T delta S? Well, similar to our first scenario, this would be negative. Okay, so let's plug that in up above. So if we have a negative enthalpy and a negative T delta S, what is delta G? Negative. So this will be negative at all temperatures as well. So it's going to be spontaneous at all temperatures. Oh, and I should have written spontaneous for high temperatures up above. All right, and then our last scenario, if delta H is negative and delta S is negative. So if delta S is negative, what is negative T delta S? Positive. So that's kind of similar to our second scenario up above. Okay, so let's plug that into our equation. So we have a negative enthalpy and a positive negative T delta S. Well, this looks a lot like what we originally talked about, right? We asked if delta H is negative and delta S is negative, what is delta G? And we said that it depends on the magnitude of the temperature. Okay, so let's think about this for a second. When would delta G be negative? So when would this be spontaneous? Would delta G be negative at high temperatures or at low temperatures? It would be negative at low temperatures. So looking at our equation, if the temperature is really, really small, that's going to make that full negative T delta S really, really small. So then delta H will be bigger in magnitude and it's negative. So that will make delta G negative. So delta G will be negative at low temperatures. So it will be spontaneous at low temperatures. Okay, so this was just a lot of Gibbs free energy review. So we'll stop here. This table down below might come in handy on your homework. And I'm actually going to highlight every other row just so we don't mix up the rows there. So I encourage you to do the same or draw lines between each row just so you don't mix up those pluses and minuses. So you might see a couple questions like this on sapling. So these are good to have handy. And in the next video, we're going to talk about reaction equilibria. So we're going to talk about the equilibrium constant. And then we'll also talk about the Van't Hoff equation, if you remember what that is. So I will see you then.